Questions 11 through 20 on the 2020 Grade 12 AMC 12B. As shown in the figure below, 6 semicircles lie in the interior of a regular hexagon with side length 2, so that the diameters of the semicircles coincide with the sides of the hexagon. What is the area of the shaded region inside the hexagon but outside all of the semicircles? Now it helps to remember some formulas. Area of a hexagon is 3 root 3 over 2 times a squared, where a is the side length. In this case, the side length is 2, so that's going to be 3 root 3 times 2 squared over 2, and that is 6 root 3. So that's the area of the entire hexagon. Now the area of the shaded region, AS, that is basically going to be the area of the hexagon, which is 6 root 3, minus the area of the unshaded region. Now, what is the unshaded region? That is what we have to figure out. And I will label this very carefully to sort of illustrate our strategy. The first thing we're going to do is draw a line from that point to that point. And then I'm going to connect those two like that. And as you can see, if you were to draw another red line there, that becomes a trapezoid. And because it's called a trapezoid, I'll just label that as T. So I'll just put a small t there. And if you do that throughout the diagram, you will create the same sort of trapezoids everywhere else. So we have how many trapezoids? 1, 2, 3, 4, 5, 6 of them. So we obviously have to subtract 6t from the area of the hexagon. But if you look closely at this diagram, the trapezoids are not the only part of the unshaded region. The unshaded region has also something small. You might have missed it. These guys right here. Those little guys, as you can see. And there's 6 of those. And each of those, I'll just call B, let's say. So if I can squeeze a B in here like that. So there's 6 of those, so I have to subtract those as well. Okay, so that is my strategy. If I can figure this out, I should be able to figure out the question. Now, there's one section right here that's a little bit outside the trapezoid. As you can see, that part right there. I'm going to call that A right there. So it was this part. Now, one semicircle, one full semicircle, which of course would be pi r squared divided by 2, is equal to, now pay attention, it's 2 of those a's, because there's an a on this side right here, and this is b, that little guy. So 2a plus b plus t. And therefore, pi, well, r is going to be just 1, because this whole thing is the diameter, which is 2. So that just becomes 1 squared, which is just 1. So pi over 2 minus 2a is equal to b plus t. And if you look over here, this is essentially 6b plus t. If we were to factor out a 6, it would be just t plus b here. So if I can figure out this, I can just sub it into there. So all I have to do now is figure out a. If I figure out a, I'm done with my question. Okay, and just to recap, here is a right here, this segment. All right, so I'm going to draw a here, this segment right here, just to use that part of the diagram because it's all symmetric. So that's a. Now I want to calculate a. So I wanted to blow this up a little bit. I basically just took this semicircle and blew it up because I think I might need a little bit more larger of a diagram. Okay, so again, let's put in our a and let's figure out what a is. So this is a right here. Okay, so how do I figure out a? That takes a little bit of thinking here. This is a very symmetric diagram, and that's helpful. So what we can do is we can put a line from the center of that diameter to that point, and I think that should be good enough. And then I'll draw a line from that point down to the base like this to make it perpendicular, like that. So that's a right angle. Okay, let's label this now. This is 1 because the whole length is 2, right? So the diameter is 2. So this is 1, and therefore this is 1. And therefore this from here to here is a half. So let's just label that. That is a half. And then from here to here is representing a radius of the circle or semicircle. And the radius is 1. And this is a right angle. So using Pythagoras, you can easily figure out this side, or some of you already know this is a 30, 60, 90 triangle. So that's going to be root 3 over 2. Now, even if you didn't know that and you just want to call it h, you can easily figure out h. It'll be plus 1/2 squared is equal to 1 squared. So h squared would be 1 minus a quarter, which is 3 over 4, and therefore h would be root 3 over 2. All right. So now I still haven't figured out a, all this math here. How do we figure out a? Well, a is basically this segment right here, this pi segment, so pi, minus this triangle. If I subtract the triangle, all I'm left with is a, so minus that triangle. So a, the pi segment, well, I need an angle. Well, it's a 30, 60, 90 triangle because h is equal to root 3 over 2. So I can easily label those angles. This is 60, and then this is 30. So the pi segment is 60 over 360 pi r squared. And then the triangle is 1/2 base times height. The base is from here to here, which is 1. And the height we just figured out was root 3 over 2. So this is, r is, what's r? R is 1. So this is just going to be pi over 6, and this is root 3 over 4. Okay, I'm set. I have a, I can figure out this now. So that's pi over 2 minus 2a, so 2a would be pi over 3, and be careful now, it will be plus root 3 over 2, and that's my b plus t. And therefore b plus t is going to be equal to 1/2 minus a third is 1/6. So that's pi over 6 plus root 3 over 2. All right, I've got that. Sub it in. So that's 6 root 3 minus 6 times pi over 6 plus root 3 over 2. So that becomes 6 root 3 minus pi, and that's minus 3 root 3, and that is 3 root 3 minus pi. There we go. And like I said, there's several other strategies, but I like this sort of method of explaining it. 3 root 3 minus pi is D for number 14. Let AB be a diameter in a circle of radius 5 root 2. Let CD be a chord in the circle that intersects AB at a point E, so that BE is 2 root 5 and AEC is 45. What is CE squared plus DE squared? Let's draw a diagram. And here is the circle, and there's the diameter. And we've got some chord, not entirely sure where it is, but let's just say it's something like that. So let's label this now. We have AB as the diameter, and then we have the chord CD. And the point where it touches each other is called E. Now what I'm going to do is draw the center right there. That's the center of the circle. And I'm going to connect two lines. So one from C to the center, like that. And another one from the center to D, like that. So essentially what I've done is created an isosceles triangle. And then I'm going to draw one final line that is the altitude of that triangle. So that is a right angle right there. Okay, so now let's do some more labeling. This is, of course, the radius of the circle, which they told me is 5 root 2. This is also the radius of that circle. And then from C to E, this distance right here, I will just call that x. And then from e to d, I'll just call that y. So essentially what they are asking me to find out is x squared plus y squared. All right, and any other labeling I can do? Yeah, I think so. From here to here is r. From here to here is r. From here to here, I will just call that d. And therefore from there to there, that's going to be r minus d. And then one last is going to be this guy, that altitude. That one, let's see here. I think I'm going to have to use this angle. So AEC, where is AEC? AEC is this one. That's 45 degrees. So if that's 45 degrees, then since this is 90 degrees, this is also 45 degrees. Now I know it's not drawn to scale, but that basically means that this is the same as that if it was drawn to scale, but it's not. So again, to repeat, AEC is 45, so this angle is 45. This angle is 90 degrees, and therefore that means that's got to be 45 also, since the sum of the angles have to add up to 180. So if I can call this side A and this side A, then that basically means that A squared plus A squared is equal to D squared. And therefore 2a squared is d squared. So a squared is d squared over 2. So a is d over root 2. Okay, so instead of that a, I can just put d over root 2. D over root 2. And that's that side right there. Okay, we, I think, are pretty much set. Now, before I start the question, I have to explain somewhat of a strategy, otherwise it will seem a bit abstract as to which direction I'm going in. We want to figure this out, right? Now, one thing is that some of you are very good at this, is rearrangement of polynomials. X squared plus y squared. Well, I have x here and I have y here. One way is to square x plus y. Another way is to square x minus y. Correct? When you square, for example, x minus y, you get x squared minus 2xy plus y squared. And therefore, if we were to isolate for x squared, y squared, it would be x minus y squared plus 2xy would be equal to x squared plus y squared. So that's my strategy. I'm going to try to get it into this format. So here we go. Now the first thing, of course, is the power of point theorem. And we're going to use that. So on this line and on this line. So that's going to be that x times y is equal to r plus d times r minus d. And that basically gives me that x times y is r squared minus d squared. All right. Now next we're going to use the law of cosines. And we're going to use it on two triangles. The first one is OEC, triangle OEC, and then triangle DEO. So OEC, on that, it'll be r squared is equal to d squared plus x squared minus 2xd cos 45. And on triangle DEO, it's going to be r squared is equal to d squared plus y squared minus 2dy. That angle will be cos 135, 180 minus 45. All right. So now let's take these two and subtract them. And when I do, on this side I'll get 0. On this side I get x squared minus y squared. Okay, I like that. And then this will be cos of 45 is 1 over root 2. So that's 2 over root 2, which is just root 2. So root 2 xd. And then cos of 135, that is also the same, except the sign is different. So that's going to be negative. That will become positive, and when we subtract it, it will be a negative. So minus 2d root 2 dy. Okay. The x squared minus y squared can factor. This one, if you take out the root 2d, becomes x plus y. And then now this nicely factors x plus y, x minus y minus root 2d. So therefore, this must be equal to 0. So x minus y is equal to root 2d. All right, great. So now, as promised, we go back and we use this relationship that x squared plus y squared is equal to x minus y squared plus 2xy. So x squared plus y squared, x minus y squared, that's going to be root td squared plus 2xy. Well, xy is that, so 2 times r squared minus d squared. This is 2d squared plus 2r squared minus 2d squared, so that's 2r squared. R we had figured out, well, we didn't even need to, it was given in the question, 5 root 2. So that's 2 times 5 root 2 all squared. So that's going to be 25 times 2, which is 50, and therefore that is 100. 100 is the answer to this question, number 12. That would be E. Which of the following is equal to the square root of log 6 to the base 2 plus log of 6 to the base 3? Well, let's see here. Let's simplify this a little bit. So I have log of 6 to the base 2 plus the log of 6 to the base 3. Using log rules, the log of 6 can be broken up, since it's the log of 2 times 3. It can be written as the log of 2 plus the log of 3 to any base. So that's going to be the log of 2 to the base 2 plus the log of 3 to the base 2, like that. And then very similarly, the log of 6 to the base 3 can be broken up into the log of 2 to the base 3 plus the log of 3 to the base 3, all under the square root sign. Okay, well, this guy is just 1, and this is just 1. So now I just have 1 plus log of 3 to the base 2 plus the log of 2 to the base 3 plus 1, all under the square root sign. So I'm going to make a substitution now. I'm going to make, let's see here, I will let the log of 2 to the base 3 be equal to a. And therefore, using log rules, the log of 3 to the base 2 is equal to 1 over the log of 2 to the base 3. So that's going to be 1 over a. So coming back here, the 1 and the 1, we'll just put that together. Log of 3 to the base 2 is 1 over a. The log of 2 to the base 3 is a, all under the square root sign. All right, now we can add all these up, get a common denominator, multiply top and bottom by a, and a. So that's going to be a squared plus 2a plus 1 over a, all under the square root sign. The top will become a plus 1 all squared. And then now that becomes just a plus 1 over root a, like that. So this, if we break it up, a over root a and then plus 1 over root a, like this, it is a over root a is just root a and then plus 1 over root a. So root a looks like, if I substitute back in, the log of 2 to the base 3 under the square root. And this is the same as that, which would be just that, the log of 3 to the base 2 under the square root. So log of the square root of 2 to the base 3 plus the log of the square root of 3 to the base 2. And that is D for number 13. Bella and Jen play the following game on a closed interval 0n of the real number line where n is a fixed integer greater than 4. They take turns playing, Bella going first. At his first turn, Bella chooses any real number in the interval 0 to n. Thereafter, the player whose turn it is chooses a real number that is more than 1 unit away from all numbers previously chosen by either player. A player unable to choose such a number loses. Upon using optimal strategy, which player will win the game? Let's tackle this. I don't think the number n matters with regard to what it is, whether it's 5, whether it's 10, whether it's odd or even. So I'm thinking that C, D, and E are wrong because it won't matter if it's 1,000 or 100. Somebody will win and somebody will lose. So let's tackle this based on that assumption. So when we create a number line, and we have, let's say, 0 and n, and Bella goes first, right? Okay. And then to optimize the strategy, Bella will go and choose a number that's exactly half, kind of maximize his strategy of winning. So that's where he chooses, that's the first integer. And then the next one, of course, is Jen. And Jen will somewhere, we don't know where. So here's Jen. And let's just say that is a number x. And one thing we know for sure is that this interval right here has to be greater than 1 according to the rules of the question. And then Bella now has to go. And this interval right here is n minus x. So all Bella has to do is just plant or choose a number somewhere in there, and that will be sufficient to meet the criteria of the question. So basically, by symmetry, if Jen's move is possible, Bella's move is also possible. So for example, this segment was greater than 1, and therefore this segment is also greater than 1 right here. And thus the first player to be unable to make a move will always be Jen. And thus she will lose. So basically, Jen will always be the first person to run out of a number to choose. Since if Jen's move is possible, then the very next move is Bella's, and that is also possible by symmetry. So therefore Jen will always lose, Bella will always win, and therefore the answer is A. There's a great book that goes through these kinds of problems, and I highly recommend it. And the book is called Winning Ways for Your Mathematical Plays. It's by Elwin Burley Camp, John Conway, and Richard Guy. And I'm sure you can get it on Amazon or any bookstore online. There are 10 people standing equally spaced around a circle. Each person knows exactly 3 of the other 9 people. The 2 people standing next to her or him, as well as the person directly across the circle. How many ways are there for the 10 people to split up into 5 pairs so that the members of each pair know each other? All right, so we are going to do this in a diagrammatic way, and here we go. So here's the diagram, and I'll walk you through it. The required pairings are sets of 5 of the 5 line segments. So as you can see, they've drawn a circle, what looks more like a Ferris wheel, but basically each of those 10 numbers would go around. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. And let's just say, give it one example. Person 2 knows 1 and 3 because those are the people next to him or her, and he also knows the person directly across, so he would know 7. And that's what those line segments represent, those red lines, those diagonals. So let's talk about them in terms of the diagonals. So let's say we have this scenario right here. And we use all 5 of these diagonals, 1, 2, 3, 4, and 5. All those diagonals are used. And that means we're using 5 diagonals, where each diagonal represents a pair. Well, that would basically mean that we would have 1 with 6, that's this diagonal. Then you'd have 2 with 7, and then 3 with 8, and then 4 with 9, and finally 5 with 10. And there's only one way of creating such a scenario. That's the scenario. Okay, so that's pretty straightforward. Now, how about 4 diagonals? 4 diagonals doesn't work, because if I use 1, 2, 3, 4, there's only 2 people left, 10 and 5, so they must go together. So 4 diagonals is basically like 5 diagonals. Now let's move to 3 diagonals, which is what this is illustrating. 1, 2, 3. And not only is it 3 diagonals, but it's also 3 diagonals in a very specific form. And you'll notice that the endpoints are consecutive. 1, 2, 3. 3 endpoints that are consecutive like that. So not only do you have 3 diagonals, you have 3 diagonals with endpoints that are consecutive. Otherwise, it doesn't work. Okay, that takes care of 1, 2, 3, 4, 5, 6 people. But what about the other 4? Well, then you have to use those 2, and we call those sides, I guess, whatever you want to call them. So 3 diagonals and 2 sides. Okay, so if I were to label this 1, 2, 3, one such example would be the 2 and the 7, the 3 and the 8, the 4 and the 9. Those come from the diagonals. And then from the sides, you get 10 and 1 and 6 and 5. So that is one way of doing it. But you can choose this in different ways. There are 5 different ways of doing this scenario. The next scenario is the one next to it, obviously. And that one is as follows. Here we only have 1 diagonal. Because if you use 2 diagonals, it's not going to work. If you use 2 diagonals, you won't be able to pair up people as directed by the question stem. So 1 diagonal is next, as this is clearly illustrating there. So again, if you use that, you'll have to use 1, 2, 3, 4 sides as that diagram shows. And from this we can make the pairs. Let's label it first. And from those 5 possible diagonals, I chose 1, right? So how many ways are there to choose 1 from 5? 5 ways. So that's why there's 5 different ways that you can make this scenario. And then the final scenario, which is next to it, that essentially involves just all sides. So there's 0 diagonals here, just 5 sides. And 5 sides, I'll label them. And this is one way. And the other way would be the other guys. So for example, this and this and this. So it would essentially just be 2, 3, 4, 5, 6, 7, 8, 9, and 10 and 1. So as you can see, there's 2 of those. So now we just have to add 1, 5, 5, and 2. And when you do, you get 13. So number 17, the answer is C. An urn contains 1 red ball and 1 blue ball. A box of extra red and blue balls lies nearby. George performs the following operations 4 times. He draws a ball from the urn at random and then takes a ball of the same color from the box and returns those 2 matching balls to the urn. After 4 iterations, the urn contains 6 balls. What is the probability that the urn contains 3 balls of each color? So we want a final result that's R, 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 blue, blue, blue. Now we initially started with just 1 R and 1 blue. So we have iteration 1, iteration 2, iteration 3, and iteration 4. And after the fourth iteration, we want this kind of scenario, 3R and 3B. Okay, that obviously means we've added 2 R's and we've added 2 blues. But that can be done in a few ways. You add an R, you add an R, you add a blue, you add a blue. That would do it. But there's also RB, RB. You see what I mean? Like the order can be reversed. RB, BR, that's another way. And then, of course, BRRB, BR, BR, and finally the last one would be BBRR. So there's 6 different ways of getting to this possible end result. So let's just calculate the probability for one. And I'm pretty sure that the probabilities are the same for each of these. So let's see what it is. Okay. Initially, there's one R and one blue. I'm concentrating on this guy. So I want the next one to be an R. So the probability that I pick an R is a half. And when I do, it becomes R, R, and B. Now again, the next one I want it to be an R. So the probability that I pick an R here is 2 out of 3. So 2 out of 3 goes there. Now I have an R, 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 and a B. Now I have to pick a B. So the probability of getting a B here is 1 out of 4. And then finally, I've got to pick another B. So first let's just write down what it becomes, R, 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 B, B. And I've got to pick a B, and I do that here. Of those 5, so 2 out of 5. And then I end up with my desired result. So now I've got to combine these probabilities by multiplying these probabilities. So that's going to be 1 over 2 times 2 over 3 times 1 over 4 times 2 over 5. And that is 1 over 30. So the probability of this is 1 over 30. And I'll let you do all these other ones because it's going to be exactly the same. The good news is they're also all 1 over 30. So that makes it very nice. All you have to do now is add up these guys. So plus, 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 plus. And when you do, you get, what is that, 6 over 30. And 6 over 30 in lowest terms is 1 over 5. So number 18, the answer is B. How many polynomials of the form x to the 5th plus ax to the 4th plus bx cubed plus cx squared plus dx plus 2020, where a, b, and c are real numbers, have the property that whenever r is a root, so is -1 plus root 3i over 2 times r? Well, by Vietas, we know that the product of the roots is going to be equal to minus z over a. And in this case, that is 2020 over 1, which is, of course, just 2020 minus 2020. So keep that in mind. The product of the roots is going to be minus 2020. Now, we have a very interesting situation. We have a polynomial of 5th degree. So there's going to be 5 roots. And I'll call those 5 roots x1, x2, x3, x4, and x5. And when you multiply them all, that product, as we have just discovered, is going to be negative 2020. Now, notice one very important point, that a, b, c, d are real numbers. So when these roots are all placed, and you do all the multiplications and multiply them by the coefficients, and then add 2020, you're going to eventually get 0. So you're never going to have any imaginary part in there. There's an imaginary part in the root, but there's no imaginary part in the solution. So what happened there? And I think that is illustrated best by the product, actually, because the polynomial has real coefficients, all normal roots appear in complex conjugate pairs. And that, I think, is best illustrated by the product, because if all the roots are going to have a variation, some have a imaginary part and some don't have an imaginary part, blah, blah, blah. But when you multiply them all together, the result is just a real number, minus 2020. You see, there's no imaginary part. There's nothing something I. So that means the i's canceled out. All imaginary parts, I am, canceled out. Now, how is that possible? It's possible if you have conjugate pairs. So, for example, if you have a plus bi, you've got to have its conjugate, which is a minus bi, as another root. And when they multiply them together, if you multiply this, for example, by that, it becomes a squared minus b squared times negative 1 plus b squared, like that. And you notice how there's no imaginary part in that. And that happened because these are conjugates. So that makes me think of the following, that we've got these roots x1, x2, x3, x4, and x5. And two of these, there's got to be two pairs of conjugates. So, for example, this one and this one are conjugates, and this one and this one are conjugates. And then this one has got to be real. So no imaginary part. That's the only way the product would eventually be a real number. Okay, well, they told me that one is r, so let's just go with that. Let's put that there. That's r. And then the other one is this, which is negative 1 plus root 3i over 2 times r. And then this must be the conjugate of this. It has to be, because of what I've explained already. So that's going to be negative 1 minus root 3i over 2 times r. And then we have two more. Now, what are those two more? I have no idea. What is x4 and x5? But they're saying that this has to be one of the roots. Okay, let's make it a root then. Let's make it another root. I don't see why not. So we put that again as x4. And then therefore x5 must be the conjugate of this. It has to be in order for the imaginary part to cancel out. So there we go. That is negative 1 minus root 3i over 2 times r. All right, that's pretty decent, I think. So here we go. That's a very reasonable way of getting a polynomial. Okay, so that product will be r times negative 1 plus root 3i over 2r times negative 1 minus root 3i over 2r. And then this, it looks like it just happens twice, right? So I can just put this twice, like that, because this is going to happen again. And that is negative 2020. Okay, let's do this math. So negative, this r times that r, that's just going to be r squared. So that's going to combine with this to give a r to the power of 3. And then we've got to square it again, because remember, this and this has to now be squared. So it's actually r to the power of 4 with this r. So it's actually r to the power of 5. So we got that. And then now we just have to figure out what is this times that. Okay. So negative 1 times negative 1, that's 1. And then the second and third term cancel. That's what conjugates do. And then when I multiply that and that, we get negative 3i squared. I squared is negative 1, so plus 3. And then the 2 times 2 is 4. So looks like that's 4 over 4, which is 1. So we got a very nice final result that r to the 5th is minus 2020. And r is a real number. So that means that r, well, I guess it's the 5th root of minus 2020. So whatever that works out to be. Okay, great. So now I've got to figure out the polynomial. Well, we have a polynomial of the form 0 is equal to x minus the first root, which is x1, and then x minus the second root, which is x2, and then x minus the third root, which is x3. And the way I did it up here, this is just 1 because that's r, and then for x2, that is going to be that x2 actually has the same value twice, so this is going to be squared, and this is also going to be squared. So this will give me one polynomial. And you can interestingly get the exact same result is if you have the following. If you have r, r, r for x1, x2, x3, and if you have x4 as this negative 1 plus root 3i over 2r, and x5 is the conjugate of that, minus 1 minus root 3i over 2. If you do that and you did the multiplication, it would end up being the same. So this is also completely valid because this multiplied by that, since they're conjugates, would cancel out, and then you just get r to the fifth. So that would give me 0 is equal to x minus x1 to the third times x minus x2 times x minus x3. And this is the only other way of doing this polynomial. So this is the second polynomial. And therefore, the total number of polynomials I'm able to get are this one and that one, so just 2. So that means number 17, the answer is C. In square ABCD, points E and H lie on AB and DA respectively, so that AE is equal to AH. Point F and G lie on BC and CD respectively. Points I and J lie on EH, so that FI is perpendicular to EH and GJ is perpendicular to EH. See the figure below. Triangle AEH, quadrilateral BFIE, quadrilateral DHJG, and pentagon FCGJI has each an area of 1. What is FI squared? Each has an area of 1. This has an area of 1. This has an area of 1. This has an area of 1. That has an area of 1. So that means the total square has an area of 4. And if the side of the square is, say, S, then S squared is 4, and therefore S is 2. So the side of the square is 2, like that. Okay, now this they have told me is equal to that. AE is equal to AH. So I can just call it something, whatever you want to call it. Let's call it A. And therefore by Pythagoras, A squared plus A squared will be equal to HE squared. And an easier way to figure out the value of A is just use the fact that this triangle has an area of 1. So 1/2 base times height, which would be A times A, is equal to 1. So A squared is equal to 2, and therefore A is equal to root 2. So I'll put that in here, root 2, it's equal to root 2. All right, so now where do we go from here? Well, we need to figure out some more distances. I can now figure out HE up here. Since A is root 2, that's going to be 2 plus 2 is equal to HE squared. And therefore, that's 4, so HE is equal to 2. And that's HE is this distance right here, from here to here. All right, what else can I figure out? At this point, I'm going to draw a line that they didn't draw, and that's a diagonal from A all the way to C. And just label where it crosses this line, that point right there, I'll just call that N for now. Have to use some letter. And then I'm going to cut this part down like this to join G to F. Now, I can figure out the distance from A to N using the fact that that is perpendicular, so it can behave as a height for that triangle AEH. So very similarly, 1/2 base times height, 1/2 base HE times height AN is equal to 1, because that 1 is the area of that triangle AEH, according to the question. So that means HE is 2, 1/2 AN is equal to 1, so AN is equal to 1. All right, so we're making some progress here. Now at this point, my strategy is to involve this trapezoid, CNIF, that trapezoid right there. Now, it's half of this pentagon, and the pentagon, they told me in the question, has an area of 1. So CNIF would have an area of half of that, so that's a half. Now, how do you figure out the area of a trapezoid? If you remember, area of a trapezoid, I'll just draw a simple example here. Let's say we have a trapezoid, and this is A, and this is B, and this is H. The area is A plus B over 2 times H. So in a very similar way, if you look at this guy right here, we are going to write it in the same way. But first I need to figure out some of these sides. The distance from here to here, Fi, I'm going to call x, and therefore the distance from here to there is also going to be x. So that is going to be from there to there. So this point right here, I guess I'll have to label it. I'll just call it P, this point right there. All right. So now we have to look at angles very briefly. This is an isosceles triangle. So that means this is 45 and this is 45, the degrees. Now, if you look at it, this was obviously a right angle since that's corner of a square. Now, since these lines are perpendicular right there like that, and then therefore obviously this is a right angle because that's a corner of a square, this angle therefore has got to be 180 minus 45, which is 135, right? And therefore we can figure out this angle, since the sum of all those angles would be 2 times 180 because those are two triangles. And we already have a 90, a 90, and a 135. So that can easily be figured out. It would be 360 minus 90 minus 90 minus 135. And therefore that is 45 right here. Well, we know that this is 90. And therefore this little guy in there has got to be 45 degrees, this angle right here. And by the same sort of principle, this will be 45, or even if you didn't know that, since that's 90, this has to be 45. So this is isosceles also, this little guy, because of that angle chasing that we did. So that means this is going to be the same as that in terms of the length. And in addition to that, because this is 90 degrees, this will be 90 degrees, and therefore now this is 45 and that's 45. So again, we've got another isosceles triangle, so this is the same as that. So all of that to show that CP is the same as PF in terms of its length. All right, so I think we're ready to start tackling the area of the trapezoid. We're going to need some lengths though. First, we're going to have to calculate the lengths before we substitute it into a formula. The first length I want to figure out is AC, which is the diagonal, and that's easy. That's just going to be AC squared is 2 squared plus 2 squared. So that means AC is root 8, which is 2 root 2. Okay, simple enough. And then now I can figure out CN. CN is AC minus this distance, AN. And both of those we know. A all the way to C we just figured out was 2 root 2. And AN we had previously figured out was 1. So CN is 2 root 2 minus 1. Now let's figure out at least one of these. Let's figure out the value for PF or CP, either one. CP is going to be that entire diagonal, which is root 2, minus this one minus this x. So minus x minus 1. And that entire diagonal is actually 2 root 2. Right, AC is 2 root 2. Okay, so I think we're ready. So here we go with CNIF right here. Using that formula, it's going to be this plus that over 2 times that height. So that basically boils down to Cn plus Fi over 2 and times the height, which is Pf. And that is equal to 1/2. Well, Cn, what do we have here? 2 root 2 minus 1. Fi is x, so plus x over 2. And then Pf, what do we have? Do we have anything? Well, Pf we concluded was the same as Cp, and Cp is right here. 2 root 2 minus x minus 1. And that all equals 1/2. Okay, so I think the halves will cancel, so all we'll be left with is just multiplying that out. And I'm going to rearrange this ever so slightly. I just switched those to make it a little bit easier when I expand it. Okay, let's expand it now. So it's going to be 2 root 2 minus 1 squared. And then the second term and the third term will cancel, and then it'll be minus x squared, and that is equal to 1. So that basically means that x squared will be this 2 root 2 minus 1 squared minus 1. Let's expand that. So that's going to be 8 minus 4 root 2 plus 1 minus 1 is x squared. So that is 8 minus 4 root 2, which is x squared. Now x was used to denote Fi, so that is basically Fi squared. And that's exactly what they wanted us to figure out. 8 minus 4 root 2. So number 21, B is the answer. Square ABCD in the coordinate plane has vertices at the points 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. Consider the following 4 transformations. L, a rotation of 90 degrees counterclockwise around the origin. R, a rotation of 90 degrees clockwise around the origin. H, a reflection across the x-axis. And V, a reflection across the y-axis. Each of these transformations maps the square onto itself, but positions of the labeled vertices will change. For example, applying R and then V would send the vertex A at 1, 1 to negative 1, negative 1, and would send the vertex B, negative 1 to itself. How many sequences of 20 transformations chosen from LRHV will send all of the labeled vertices back to their original positions? All right, so we're going to need a lot of space for this. So here we go. Now let's say I've got a basic sort of diagram that shows the coordinate plane. So this is point A, B, C, and D, right? This is the x-axis, this is the y-axis. All right. Now, we have to have 20 transformations. So 1, 2, 3, 4, ... You get the point. 20 of them. Now, each of these has 4 possible choices. It could be either L, R, H, or V. So I've got 4 choices here, 4 choices here, 4 choices here, and so on. So when you multiply them all, that's how many different combinations there are, and that's 4 to the power of 20. Now all the answer choices are in powers of 2, so I'm going to just immediately convert that to a power of 2, which is 2 to the power of 40. And interestingly, as you can probably see, all the answer choices are less than that, which makes sense because this is the absolute total. It would make sense that since we have some restrictions, our answer would be less than that. Okay, so far we're on the right track. Now, what I'm going to do is just concentrate on what happens when I make a transformation for one of these. So let's just choose A. what happens to A when I make each of these transformations? Well, L is, what is L actually? I think I forgot. It's a rotation 90 degrees counterclockwise, okay? 90 degrees counterclockwise means it would basically go from there to there. This is 90 degrees. So it would end up at B. All right, so it would go to B. Now R, 90 degrees clockwise, so it would go from here to here, where this is 90 degrees, so D. And then I think x-axis and y-axis are relatively easy, so this goes to D. X-axis, reflection in the x-axis, well, that's easy, it just go to D. And then across the y-axis, it would go to B. Okay, now that's just for one move. We've got a whole bunch, we've got 20, right? What happens when I do a second move? So, B now. B for L, for R, let me do it horizontally. For L, for R, for H, and for V. What happens? Okay. So let's figure this out. When B is going to be rotated, it will end up from there to there, where this is 90 degrees. So it'll end up to C. And then when it's rotated the other 90 degrees in the other direction, it'll go to A, like that. And then reflected in the x-axis, B will end up at C when it's reflected there. And then when it's reflected in the y-axis, it'll end up at A. Okay. So, in a very similar way, I'm not going to talk you through every single one. I'll just let you figure this out for L, R, H, V. D would go to A, C, A, C. And then again, it's the same D, so A, C, A, C. And then B, we already did C, A, C, A. So after two moves, notice that this original A ends up at A half of the time. So there are 16 possible ways it could end up, and half of them, 8 of them, it ends up at A. But that's only after two moves. If you keep doing this, you'll notice that in general, after an even number of moves, it will end up at its original position half of the time. Okay, so that is very important. Now, I would like to do the exact same thing, but this time for B. Because I've already done it for A, and I'd like to see what happens with B. And I'm also going to conclude, before I even start B, that with this scenario here that I did for A, C will always be in the opposite quadrant. So if A ends up back in here, C will end up back there. That will be basically helping to put the original shape back into its original position. All right, so let's do the exact same thing, but this time we'll do it for B. So I think we'll be able to do it with this much space here. Okay, so here we go. So this time for B now, we have L, R, H, and V. And we're going to start and see what happens with B. And I won't talk you through it, I'll just write it out. So B will go to C, B will go to A, B will go to C for this one, and B will go to A. Now that was just the first move. What if I have a second move? And then for the second move, again, it will be L, R, H, V, and let's write it out. C will go to D, B, D, B. A will go to B, D, B, D. C will go, well, that one I've already done. And A will go to, I've already done that, B, D, B, D. I think there was a slight discrepancy there where I think this column is V and this is H. It doesn't really matter because the gist of it will not be different. So what did I show here? Exact same thing, that after 2 moves you end up at the same position half the time. There's 16 possible positions as I've listed, and 8 of them are B's. So just like I wrote here, after 2 moves, and in general after an even number of moves, it will end up at its original position 1/2 of the time. So the same story here. 1/2 of the time you will be back into the original position. Okay, and just for the sake of completeness, I've got to write in, just like how I did here, that D will be in the opposite quadrant. Okay, so now what we do is we take our total, which was 2 to the power of 40, and we take into consideration that half and that half, that we have to multiply by a half to bring it back into its original position, and then we have to multiply by a half again to bring B back into its original position. This brings A back into its original position, then this brings B back into its original position, and we have to have an even number of moves, and we do because we have 20 moves. That is what they told us in the beginning of the question. So this becomes 2 to the power of 40 over 2 to the power of 2, which is 2 to the power of 38. And therefore, number 23, the answer is C. 2 different cubes of the same size are to be painted, and with the color of each face being chosen independently and at random to be either black or white. What is the probability that after they are painted, the cubes can be rotated to be identical in appearance? So I'm going to try to explain this in a very complete way because it's a good question. So let's label these now. Let's see here. I'm going to label the sides. So top will be 1, bottom will be 2, and then this side 3, this side 4. The very front I will call 5, and the very behind I will call 6. All right. So now we have to make a table and look at the different scenarios. So here is the scenario, and then this is the total number of cases, and these are the cases where they are identical. So the first scenario is when you have the first cube having 0 black sides and all 6 sides are painted white. And the same thing is true here. In order for them to match, they have to at least first start off with the same number of black and white. That's sort of the basic criteria. And then the second criteria is that the rotation has to be the same. Okay, if there's 0 black and 6 white, that means there's only one way of making that for each cube. So 1 times 1. Basically a cube where everything's painted white, and that's just 1. So the cases that are identical, well, again, the one cube that's all white and the other cube that's all white, they're identical. So there's one case. So that starts off pretty straightforward and easy. Okay, now we move on to the next one, which is 1 and 5. So again, part of the criteria is that at least we have to have the same number of black and white, and then the orientation has to be the same. So first of all, what's the total? From 6, choose 1 for that black, and from the remaining 5, choose 5, and that's just 1, so you don't have to worry about that. And then we'll multiply that by 6, choose 1 for the second cube. This is just 6 times 6, which is 36. So 36 cubes that can be made, 36 combinations of cubes that can be made. 6 for the first cube, 6 for the second cube. Now, how many of those are identical? Well, all of them. If you have a cube, think about it, that has only one black face, and the other cube also has one black face, they can always be made to look the same by changing the orientation. For example, if the black face was that side 1, and on the second cube the black face was side 4, you can just rotate it and make it look the same. So all of those cubes, 6 times 6, which is 36, will be identical. Can be made to look identical by rotation. All right, now we get into something that is a little bit different. Now we have black and white 2 and 4. So 2 sides are painted. Now if 2 sides are painted, some of you will be able to do this in your head, but if you can't, no problem. I'm going to draw them here. I'm not going to draw the cubes, but I'm going to put the different criteria. Well, first of all, how many are there? Well, from 6, choose 2 this time. 6, choose 2 is 15. And for the second cube, same thing. 6, choose 2. So it's 15 times 15, which is, of course, 225. All right. So of the 225 possible combinations, we have to figure out how many are identical. Well, let's just concentrate on one cube. That's 15 different orientations. 15 is not that many, so I can write them out. 2 sides are painted black. So those 2 sides could be either 1, 2, 1, 3, 1, 4, 1, 5, or 1, 6. Or they could be 2, 3, 2, 4, 2, 5, 2, 6. Or they could be 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and finally 5, 6. This is 15. And this is the complete list of 15 possible ways that a cube could be painted with 2 sides black. Now, of these, how many are identical? Meaning, if I have another set of 15 exactly like that, how many match? Well, there's 2 sets. The first set is when you have something like top and bottom. Top and bottom, 1, 2, right? So if I have any top and bottom, that will match with the top and bottom on the other group of 15, from the other group of 15. So top and bottoms are 1 and 2, 3 and 4. It's not really a top and bottom there, but it could be rotated to become a top and bottom, right? You just rotate that way. So 3 and 4 is a top and bottom. That's that one. And what's the other top and bottom? 5 and 6, right? The front and the back, if you rotate it that way, it'll become a top and bottom. So those 3 can match the exact 3 from the other 15 for the other cube. So 3 times 3. 3 from the first set times 3 from the second set. Those will be able to match when you rotate them to look identical. Now, how many do we have left? Well, from the 15, I just selected 3, so I've got 12 left. And those 12 all have the same sort of description in that they're adjacent, like 1 and 4. You see how they're adjacent? So 1 and 4 is just one of them. And every other one is always going to be adjacent, 2 and 3, and so on. So adjacent ones can definitely also be rotated to look the same. So there's 12 of those. So from those 12, I can match 12 from the other set of 15 to make them look identical via rotation. So this is going to be 144. All right, now we're getting into B3 and W3. B3 and W3. So this is 6, choose 3. This is 6, choose 3. And what is 6, choose 3 is 20, right? So 20 times 20, now we got 400. Okay. 400. Okay, again, we have only 20, so since this is practice, I'm going to list them all out. And hopefully that will make it a little bit more clear for you. So we got 20, so let's list them all. Now we have 3 black are painted. So that's either 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, right? 1, 3, 4, 1, 3, 5, 1, 3, 6. Then we have 1, 4, 5, 1, 4, 6, and then 1, 5, 6. All right. Then we have 2, 3, 4, 2, 3, 5, 2, 3, 6. And then we have 2, 4, 5, 2, 4, 6, and then 2, 5, 6, 3, 4, 5, 3, 4, 6, 4, 5, 6, And then 3, 5, 6 is one that I kind of skipped over. All right, so that's 20. Of those 20, I've got to start talking about how many are identical. All right. So the first thing is, let's look at, I'm going to need a little bit more space here. Let's look at scenarios where we've got a cube that has sort of sharing a corner. So this is the corner, right? So here is one where we shared a corner, and those would have been 1, 2, and 4. So 1, 2, and 4. So I will write out those kinds, the ones that share a corner. And there's 8 corners, so there's 8 corners, so there should be 8 of those. And I think I had said 1, 4, and 2. Sorry, it was 1, 4, and 5 share that corner. All right, so I got to be careful there. So let's list those 8 that share a corner. 1, 4, 5, 1, 4, 6, 1, 3, 6, 1, 3, 5, 2, 5, 3, 2, 5, 4, and 2, 4, 6, and 2, 3, 6. So in a relatively systematic way, I labeled those corners. Now, those corners can be rotated to look exactly the same as any other corner from the other set of 20. And now we look at another set. The other set are the ones that are consecutive, like this one, 1, 4, 2. You see how that's consecutive? Or 4, 1, 3. 4, 1, 3 is another consecutive one. And those can similarly be rotated to look the same. And there's going to be 12 of those. So 1, 4, 2, 4, 2, 3. And you can just kind of go around to get these 1, 4, 2, 4, 2, 3, 2, 3, 1, and then 3, 1, 4. I just went all the way around like that. And you can do the same thing going all the way around like that. So 1, 5, 2, 5, 2, 6, 6, 1, 5, and then 2, 6, 1, and then 6, 1, 5. I just wanted to keep it in order. And then you can do another set going across like this. So that's going to be 3, 5, 4, 5, 4, 6, 4, 6, 3, and 6, 3, 5. Right. 3, 4, 5, 5, 4, 6, and so on. All right, so I got 12 here. So in a very similar way, those 12 can be rotated to look exactly like the same 12 from the other set of 20. So how many got? 8 and 12, right? So 8 times 8, those guys, 64, and 12 times 12, so 144. Now finally we have some good news. The good news is that the next ones are easy because we've already done the math. This is the exact same as this, so it's also going to be the same. It's also going to be 9 and 144 for the exact same reason. The next one, which is 5 and 1, that is the same as this, and that's going to be 6 times 6 for the exact same explanation. And finally, the one where it's 6, 0, that's also going to be the same, which is just 1. Okay. All right, now finally I get to count them all. So probability question. So the total is the total number of ways. Well, I've got 6 faces. Each face can be either black or white. So 2 choices for each face. So I just have to multiply. This is the absolute total for each cube, and that's 2 to the power of 6. So that's what, 64? Yeah. So 64 for the first cube and 64 for the second cube. That's the total combinations. Now the numerator is our specific condition, which we painstakingly discovered, is this right here. All of these guys. So 1 plus 36 plus 9 plus 144. And all of those you multiply by 2 because there's 2 of them. And then add a 64 plus a 144, like that. And that is 588 over 4096 in lowest terms. That is 147 over 1024. 147 over 1024, number 20 would be D.